57th lecture. We're studying circuit analysis, and for the last couple of lectures, we are studying three-phase circuits. In the last lecture, we started studying Y-type connections of three-phase source and load. In this example, we're going to solve a simple example where we are given a line voltage VAB, line voltage VAB to equal to 208 at an angle of minus 30 volts. It's an RMS value, and we are supposed to find the three phase voltages, the set of three phase voltages VAN, VBN, and VCN. And we know that A to N, E to N, and C to N are phase voltages. We studied phase voltages and line voltages in our last lecture. So these are phase voltages. How to find these these phase voltages, the set of three phase voltages given this line voltage VAB. Right. To find that, first we have to go through a small recap from last lecture. That is that VAN, we studied VAN. If VAN is equal to some voltage VP at an angle of 0 volts, VPN, then to fulfill the requirement of a balanced three-phase system, VBN has to have the same maximum magnitude, but the phase should be 120 degrees lagging, minus 120, and VCN should be 240 degrees lagging compared to VAN and 120 degrees lagging compared to VBN. We also studied the set of three line voltages. For this phase voltage VAN and VBN, these two phase voltages, the line voltage VAB is under root 3 times VP. The magnitude is 1.732 times larger compared to the phase voltages, but it is at an angle of 30 degrees leading compared to VAN. So VAB is 30 degrees leading compared to VAN. You'll see VBN is also 30 degrees leading. VBC is 30 degrees leading VBN, and VCA is 30 degrees leading VCN. Or in other words, VBC is 120 degrees lagging VAB, and VCA is 120 degrees lagging VBC. So these three set of voltages form a balanced three-phase system, and the requirement of balanced three-phase system is also fulfilled by this set of line voltages too. Right. So coming back to the problem, we have to find VAN giving this VAB first, and then VBN and VCN. Right. Let's find VAN first. VAN is, according to our last lecture, VAN is VP at an angle of 0 volts. So we have put it here. VAB is under root 3 VP times at an angle, under root 3 times VP at an angle of 30 degrees. So we have put it here. Right. Now we can solve. This VP cancels with this VP, and VAB can be taken on the other side of the equation. VAB times 1 over square root of 3. This 30 taken in the numerator becomes minus 30 degrees. So now let's put the value of VAB given in the question. It is 208 at an angle of minus 30 degrees RMS. So let's put this value here, 208 at an angle of minus 30. And this one. Now we have two complex numbers. magnitudes and phase, and we know that when we multiply two complex numbers in their polar form, we multiply their magnitudes. 208 multiplied by 1 over square root of 3 gives us 120, and the angles are added. Minus 30 plus minus 30 becomes minus 60 volts RMS. Right. So once we have computed VAN, computing VBN and VCN is straightforward. To fulfill the requirement of balanced three-phase system, VBN, we know it has to be 120 degrees lagging compared to VAN, as we have studied here. VAN is VP at an angle of 0. So VBN is the same magnitude at an angle of minus 120 degrees lagging. So it's super simple. VAN is 120 at an angle of minus 60. So VBN should be 120 degrees lagging compared to VAN. Minus 60 minus 120 is minus 180. And we know that VCN is 240 degrees lagging compared to VAN having the same magnitude. So minus 60 minus 240 is 120 degrees. This is also RMS, and this is also RMS. So as we know that minus 300 degrees going clockwise takes us to the same point where we reach by going 60 degrees counterclockwise. Plus 60 is the same point. So 120 at an angle of minus 300, which is VCN, can also be, as we know, that we reach the same point by either we move clockwise by 300 degrees or counterclockwise by 60 degrees. So VCN can also be written as 120 at an angle of 60 degrees. Right. That's all for today's lecture. And in the next lecture, we will keep on three-phase